Dear participants of the mathematical festival, in this lecture, I will explain the solution to the problem 3. But before this, I will talk a little about representations of real numbers, because this is actually the topic of the problem. Of course, numbers form the basis of all mathematics. And one of the first questions that we learn about numbers is how to represent them. I will start with a quote by famous mathematician Laplace, who said that it is India that gave us the ingenious method of expressing all numbers by means of 10 symbols, each symbol receiving a value of position as well as an absolute value, a profound and important idea which appears so simple to us now that we ignore its true merit. But its very simplicity and the great ease which it has lent to computations put our arithmetic in the first rank of useful inventions. And we shall appreciate the grandeur of the achievement the more when we remember that it escaped the genius of Archimedes and Apollonius, two of the greatest men produced by antiquity. So he underlines the importance that numbers can be expressed using only 10 symbols. In fact, even less, as we will see today. What kind of numbers we know? Of course, you are familiar with natural numbers that we use for counting. Integers that appear when we subtract natural numbers. When we divide integers, we arrive to rational numbers. There are also irrational numbers like square root of 2. This is a number that gives 2 after we multiply it by itself. Real numbers that consist of rational and irrational numbers. And also, maybe you're familiar with the complex numbers. These are, in some sense, more artificial numbers that are obtained from real numbers by adding a special number I, such that I squared gives -1. You know that, that there is no such real number that gives -1 after squaring. But if we imagine that such number exists, we arrive to the system of complex numbers. And in fact, this is not the end. There are much more systems of more and more complicated numbers. So what Laplace meant by expressing all numbers by 10 symbols, you know that every real number can be expressed in the decimal form, which is plus or minus the integer part plus minus a0, and then the fractional part, a1, a2, a3, where a1 is the number of tens in x, a2 is the number of hundreds, a3 is the number of thousands, and so on. A simple example, if we divide 4 by 5, we get 0.8. If we divide -10, say, over 7, we get an infinite decimal expansion, but you can observe that it is periodic. So its part after dot 42857 repeats 142857 and so on. In fact, for every rational number, its decimal expansion is either finite or infinite, but periodic. However, decimal expansion, which is of course very useful in computations, is not the only one. At first, consider a special example. So consider a real number root of 2, which is irrational number. So it has infinite decimal expansion, and there is no periodicity in this expansion. However, we can find another representation of this real number in the form of a continued fraction. Observe that root of 2 can be written as 1 plus 1 over 1 plus root of 2. Indeed, if we take root of 2 minus 1 multiplied by root of 2 plus 1, okay, then we get the difference of squares, which is 2 minus 1, which is equal to 1. Okay, so now we divide by root of 2 plus 1, add 1, and get this equality. Now, in the obtained equality, I will substitute this root of 2, okay, by the whole expression that we obtained for root of 2. Since here we have 1 plus root of 2, in the denominator, we will obtain 2 plus 1 over 1 plus root of 2. And then we repeat this procedure. It turns out that if we continue this procedure longer and longer, we will get, okay. So on each step, we have an equality, yes, for the root of 2. Now, if we remove this part, we will obtain a rational number which will become closer and closer to root of 2 if we proceed with this representation. I want to say that it can be proved that root of 2 can be written as an infinite continued fraction. Once again, this means that if we write this long fraction and stop at some point, we will get a rational number which will become closer and closer to root of 2. So this is a different representation of root of 2. And in particular, you can see that it is much more regular than the decimal representation, because we have 1 plus, and then in each denominator there is 2 plus, 2 plus, and so on. Okay, this is a general fact. So every real number can be written as a continued fraction of the following form. So some integer a0 plus And we start the continued fraction, 1 over a1 plus 1 over a2 plus 1 over a3, and so on. And here, numbers a1, a2, a3 are numbers from 1 to 9. In fact, this expansion stops at some point if and only if x is a rational number. Continued fractions are not so useful in computations. However, they are useful from the theoretical point of view, which I will try to explain in a moment. But now let's look at some more examples. So 4 over 5, let's divide numerator and denominator by 4, and we will get a finite continued fraction, 1 over 1 plus 1 over 4. Also, we had an example, minus 10 over 7. Let's write it as minus 2 plus 4 over 7, and divide numerator and denominator by 4. And we get, after we also divide, after we also represent 3 over 4 as a continued fraction, we get a finite continued fraction. Okay, and one more example, root of 3. So this is the irrational number. To obtain its representation as a continued fraction, we use the same approach as for root of 2, namely root of 3 minus 1 times root of 3 plus 1. This is difference of squares, so 3 minus 1, which is equal to 2. So we get that root of 3 is 1 plus 1 divided by root of 3 plus 1 over 2. Now here in the fraction which is in the denominator, let's add and subtract 1. Okay. 1 plus 1 is equal to 2, and we can divide by 2. So we get 1 plus root of 3 minus 1 over 2. And using this equality, we see that root of 3 minus 1 divided by 2 is 1 over 1 plus root of 3. And now what we can do, we repeat this. I mean, we substitute instead of root of 3 the obtained all this representation. So since we have here 1 plus root of 3, we will get here 2. 2 plus 1 over 1 plus 1 over 1 plus root of 3. And then we repeat the procedure, so we get a continued fraction, 1 plus, and then in each denominator we have 1, 2, 1, 2, 1, 2. Okay. So why continued fractions are important? because they provide good approximations of real numbers by rational numbers. If we have, let's say, irrational number x, which is represented as infinite continued fraction, if we stop at some position an, we get a rational number xn. And as I mentioned, the greater n we take, the closer, the smaller will be the difference between xn and x. Let's look at some examples. So what is x0? X0 is just a0. And if we denote this rational number by Pn divided by Qn, then we see that P0 is a0 and Q0 is 1. What is x1? x1 is a0 plus 1 over a1. Okay, we can write this as a1, a0 plus 1 divided by a1. So P1 is a1, a0 plus 1, and Q1 is a1. Okay, now what is x2? Looks like it's more complicated. After all transformations, we get P2 equals to this expression a2, a1, a0 plus a0 plus a2. And Q2 is a2, a1 plus 1. But in fact, these expressions are not complicated because if we in the numerator, if we take a2 as a common multiple, then a2 is a common multiple near p1 because p1 is a1, a0 plus 1. And a0 is p0. So p2 is actually a2 p1 plus p0. And q2 is a2 q1 plus q0 because q1 is equal to a1 and q0 is equal to 1. And it turns out that this is a general rule. Pn is equal to an pn minus 1 plus pn minus 2. And here must be qn. Sorry for that. Qn is equal to an qn minus 1 plus qn minus 2. These expressions, they allow to estimate actually how small is the difference between x and xn. X minus xn is less than 1 divided by qn plus 1. And one can show that actually this number, 1 over qn plus 1, becomes small when n becomes large, quite fast. If x is irrational, then one can estimate the difference between x and xn even from below. And you see that this inequality is very similar to inequality 1. So expressions in the denominator of the same order. Okay, and what is more important, it can be proved, but it is not an easy result. So that if we look at all rational numbers with the denominators not greater than some fixed number, then the closest rational number to x is either its continued fraction Pn over Qn, or so-called the median of two continued fractions, Pn plus Pn plus 1, Qn plus Qn plus 1. And this fact allows to analyze properties of real numbers using like best approximations, best rational approximations. The theory of continued fractions was developed further, and in 20th century, the notion of a generalized continued fraction appeared. You see that this is an expression similar to continued fractions, but here in the numerators we have some numbers a1, a2, a3, not 1. And in general, it can be they can be complex numbers. And B0, B1, B2, and so on as well can be complex numbers. In 1994, Lerner proved that every real number can be written as a generalized continued fraction, but with the coefficients only of two types, or Bn(an) is equal to 1, 1, or Bn(an) is equal to 2 minus 1, which is somewhat unexpected result. And it is interesting that the proof uses a special function L of x, which is equal to x over 1 minus x when x is less than 1/2, and 1 minus x over x when x is bigger than 1/2. By iterations, I mean the following. So the first iteration is just L of x. The second iteration is L of x. The third iteration is L of x. 1, 2, 3, and so on. And it turned out that such results are used in a more profound mathematics like dynamical systems, ergodic theory. So if you are interested, you can read more about generalized continued fractions. So this is an object of modern research. For you to imagine, the blue function is the first iteration, the red function is the second iteration, yellow function is the third iteration. And one of the main question is if we take some number x and start applying function L to this real number x. So what sequence we will get? And we will get the sequence x, value of x, value of x, with many very interesting properties. So now let's go to the problem 3 of the festival. In this problem, we will study some analogs of generalized continuous fractions with limited possible values of coefficients b and a. The problem is the following. So we start from some set of strictly positive real numbers. Then we take all possible numbers ab from a0 and form numbers of 1 over a plus b. And all these numbers that we can get, the set of all such possible numbers is denoted as a1. And then we repeat. So take all possible numbers from a0 or from a1, a and b, and a2 will be the set of numbers of the form 1 over a plus b, and so on. Okay, if we constructed sets a0, a1, up to an, and we take all possible numbers a and b from these sets and form numbers 1 over a plus b and get the set an plus 1. And we say that a real number is a0 nice if it belongs to one of the sets a0, a1, a2. So if we can obtain this number by described procedure. So a0 is the set of numbers that we start from. Now assume that a0 is just one real number equal to 1. So the first question is, what will be the smallest a0 nice number and what will be the largest a0 nice number? Okay, this question is relatively simple. But before looking at the solution of the question, let's do some experiments. Okay, so we start from real number 1. Then we can form the number 1 over 1 plus 1, which is 1/2. Now we can take any pair of these numbers. Of course, if we take 1 and 1, we will get again 1/2. So there is no sense in doing this. If we take 1 and 1/2, we get 1 over 1 plus 1/2, which is 2 over 3. Again, if we take 1/2 and 1/2, we will get 1. Okay, let's do some more. We can take 1 and 2 over 3. Okay, so in the denominator, we have 5 over 3, so we get 3 over 5. we can take 1/2 and 2/3. So that we will get, in the denominator, we will get 7/6, 6/7. And we can take 2/3 and 2/3. We will obtain 3/4. So these are some A0 nice numbers that we can obtain. And here, in fact, we see that we don't obtain numbers bigger than 1, and we don't obtain numbers less than 1/2. In fact, 1 will be the largest A0 nice number, and 1/2 will be the smallest A0 nice number. We already saw that these numbers are A0 nice. And now let's show that actually all A0 nice numbers are rational, which is not hard to see, and belong to the segment from 1/2 to 1. We will prove this property for every number from AN, and the proof is actually easy induction. If n is equal to 0, then obviously the statement is true. Okay, assume that we proved the statement for all sets A0, A1 up to AN. Consider x from AN plus 1. Then we can write x as 1 over y plus z, where y and z belongs to the previous sets from A0 to AN. But y plus z is rational, so x is also a rational number. And since y and z are from 1/2 to 1, their sum is from 1 to 2. It follows that x is again from 1/2 to 1. As a conclusion, all A0 nice numbers are rational and belong to the segment from 1/2 to 1. Okay. The second question is more complicated. And I suggest to find actually all possible A0 nice numbers. In the first question, we saw that all A0 nice numbers are rational and belong to the segment 1/2 to 1. Let's probably recall which numbers we already obtained. Let me write it again. 1, 1/2, 2/3, 3/5, 6/7, 3/4. If we consider rational numbers from the segment 1/2 to 1, with, say, denominator 2, there are only two such numbers. This is 1/2 and 2/2, which is 1. And we obtain such numbers. If we consider numbers with the denominator 3, then there is only one such number, which is 2/3. If we consider numbers with the denominator 4, these are 1/2, which is 2/4, 3/4, and 4/4. So we obtained all these numbers. Okay. And now let's do one more step and look at real numbers with the denominator 5. There are numbers 3/5, 4/5, and 5/5. And in this small list, we still don't have 4/5. However, if we take numbers 1/2 and 3/4, we get 1/1/2 plus 3/4, which is 4/5. So we obtained all rational numbers from segment 1/2 to 1 with a denominator 5. Let's do the last experiment and consider rational numbers with a denominator 6 from segment 1/2 to 1. These are 3/6, which we already obtained, 4/6, which we already obtained, 6/6 we already obtained. We still need to obtain 5/6. This is relatively easy because we have number 3/5. And if we consider 1/3/5 plus 3/5, we get 5/6. So our experiment suggests that probably we can get any rational number from the segment 1/2 to 1. And once we made such a suggestion or hypothesis, now we can try to prove it. It is a very important step, first to understand what you want to prove, and then actually prove it. I will use the following notation. The segment 1/2 1 with the index q means all rational numbers from the segment 1/2 to 1. Okay, now let Bn be the set of all rational numbers from the segment 1/2 to 1 with the denominator n. So Bn is all rational numbers of the form m divided by n, where mn is from 1/2 to 1, which means that m is bigger than n over 2 and less than n. For example, we already actually considered these sets. So what is B1? The denominator is equal to 1, so B1 is 1. B2, with the denominator 2, we have two numbers, 1/2, 1 over 2, and 2 over 2. Okay, with the denominator 3, we have 2 over 3 and 3 over 3, and so on. And now let's prove that all numbers in Bn are A0 nice. So all numbers in Bn will be obtained if we do this, if we do the procedure of constructing A0 nice numbers long enough. And let's prove it by induction on n. The case n is equal to 1 is obvious because B1 consists of a number 1, which is A0 nice. In fact, we already proved that all numbers from B1 to B6, they are A0 nice. Now, the step of induction, assume the statement is proved for B1 until Bn minus 1, and consider a rational number from Bn. It is of the form m divided by n. M is bigger than n over 2 and less than n. Assume that m is equal to n over 2. Then it is just 1/2, and we know that it is A0 nice. Similarly, if m is equal to n, then m over n is just 1, which is also nice. So it remains to consider the case when m is strictly bigger than n over 2 and less than n, or less or equal to n minus 1. Yeah. First, assume that n is even. Means that n is equal to p for some natural number p. Our assumption on m means that m is bigger than p and less or equal to 2p minus 1. Okay, from this inequality, we infer that p is greater or equal to m plus 1 over 2, which is bigger than m over 2. It means that p is bigger than m over 2 and less than m, and m is less than n. M is less than n. But then we know that the number p over m is A0 nice. And if we take this number p over m, consider the sum p over m plus p over m, we will get 2p over m, which is n over m. But this number, 1 divided by this number, is m over n. So we proved that m over n is nice. Good. The case when n is odd is similar. So let n be equal to 2p minus 1. I recall that n over 2 less than m less or equal to n minus 1. So m is bigger than p minus 1/2 and less or equal to 2p minus 2. From this inequality, p minus 1 greater than m over 2, and p is less than m plus 1/2, but p is a natural number, so p is less or equal to m. Again, we have an inductive assumption that says us that P over M and P minus 1 over M are nice. So it remains to take these numbers and take their sum. That will give us N divided by M. And the reciprocal is M over N. We proved that if all rational numbers with a denominator 1, 2, 3 till n minus 1 from the segment 1/2 1 are nice, then all rational numbers with the denominator n from this segment will be also nice. We have found all A0 nice numbers, and these are rational numbers from segment 1/2 to 1. And the last third part, let's start from the different set A0. A0 will be equal to A0 will consist from two numbers, 1 and 2. In this case, what will be the smallest and the largest A0 nice number? Here, the approach is similar in the sense that to take, if we take the largest possible A0 nice number, which is 2, and consider 1 over 4, which is also A0 nice, then probably 1 over 4 will be the smallest. Indeed. Now, if we take 1 over 4 and consider 1 over 1 over 4 plus 1 over 4, we will get 2. So we can make a suggestion that the smallest nice number is 1 over 4, and the largest is 2. And as we did in part A, let's prove that any nice number belongs, is rational and belongs to the segment 1 over 4 to 2. The proof is similar, also is by induction on n. For A0, the statement is true. Now assume that all numbers from A0, A1 to AN are rational and belong to the segment 1 over 4 to 2. Take two such numbers, take their sum, and let x be 1 over y plus z. So x is rational, and the sum y plus z is bigger than 1 over 2 and less than 4. So x is bigger than 1 over 4 and less than 2. So 1 over 4 is the smallest A0 nice number, and 2 is the largest A0 nice number. Okay, and now let's find all A0 nice numbers in this case. Unfortunately, the approach we used in part B does not work here. Again, we can consider the set Bn, which is the set of all rational numbers from with the denominator n from the segment 1/4 to 2. Of course, we will want to prove that actually this segment is the set of all A0 nice numbers. So the condition on m and n will be n/4 less or equal to m less or equal to 2n. And here it is not clear how to use induction because, for example, for the case when n is even or odd, you can try, but I wasn't able to find the proper induction step. So we will do it the proof in a different way. And the first observation is 1 is A0 nice number. In particular, at least we already know that all numbers from 1/2 to 1 are A0 nice. Okay. And now we can take the set of all these numbers, take all possible sums, okay, and take reciprocal and get more A0 nice numbers. Let's take the largest A0 nice number, which is 2, add it to all numbers from 1/2 to 1, and then we will obtain all rational numbers from 5/2 to 3. Now take reciprocals and get that all rational numbers from 1/3 to 2/5 are nice. Okay, let's draw it schematically. Let this be the real line. What nice numbers we have from 1/2 to 1. Let this be 1/2. And this be 1. This is 2. This is 1/4. Of course, the scale is wrong here, but it's not. We only are interested in the order. Okay. And we also get numbers from 1/3, which is somewhere here, let's say, to 2/5, which is less than 1/2. Okay. Get all numbers from this segment and rational numbers and all rational numbers from this segment. Okay. If we add 1/4, which is the smallest nice number, to all numbers from segment 1/2 to 1, we obtain all rational numbers from segment 3/4 to 5/4. Take reciprocals and get that all rational numbers from 5/4 to 4/3 are nice. 5 over 4 is less than 1, but bigger than 1/2, somewhere here. Okay, and 4 over 3 is bigger than 1. So as you see, we were able to extend the segment of A0 nice numbers. However, we have a small gap here from 2 over 5 to 1/2. However, let's take the segment from 4 over 5 to 4 over 3 and take all possible sums of these rational numbers. We get all rational numbers from segment 8 over 5 to 8 over 3. And now take reciprocals and get all rational numbers from 3 over 8 to 5 over 8. Now 3 over 8 is bigger than 1 over 3. And less than 2 over 5. 5 over 8 is bigger than 1/2. So we filled this gap. Okay, once more. We were able to fill the gap because of these inequalities between A0 nice numbers. We extended the segment 1/2 to 1, but to the segment 1/3 to 4 over 3. And now the idea is to add 2 to all numbers from this segment. We will get 1/3 plus 2, which is 7 over 3, and 4 over 3 plus 2, which is 10 over 3, which means that all rational numbers from 3 over 10 to 3 over 7 are A0 nice. If we add 1 over 4 to 1 over 3 and 4 over 3, we will get 7 over 12 and 19 over 12. Which will give us that all rational numbers from the segment 12 over 19 to 12 over 7 are A0 nice. Now, 3 over 10 is less than 1/3. 3 over 7 is bigger than 1/3. Okay, 12 over 19 is less over 4 over 3, and 12 over 7 is bigger than 4 over 3. which means that we extended more the segment that consists of A0 nice numbers. And let's continue with this procedure. Now, A1 is 1 over 3, B1 is 4 over 3. And let's define an plus 1 as 1 over bn plus 2, and bn plus 1 as 1 over an plus 1 over 4. Okay, so we add like the smallest A0 nice number and we should get a bigger A0 nice number, bigger than bn. Similarly, we add 2 to bn and get an plus 1, and we should get the smaller number than an. And in this way, we will get an increasing sequence of segments A and Bn, and we will actually prove that all rational numbers from these segments are nice. Okay, for this, we need some relations between An and Bn. So first is An times Bn plus 2 is bigger than 1, and An plus 1 over 4 times Bn is less than 1. Which actually means that An is decreasing and Bn is increasing. So let's check this for n is equal to 1. A1 is 1 over 3, B1 is 4 over 3. The product is 10 over 9. Yes, the product of A1 and B1 plus 2, which is bigger than 1. Similarly, A1 plus 1 over 4 is 7 over 12. B1 is 4 over 3. The product is less than 1. Now assume that we proved the relations for n. And let's look at An plus 1 times Bn plus 1 plus 2. An plus 1 is 1 over Bn plus 2. Bn plus 1 is 1 over An plus 1 over 4 plus 2. Now let's multiply. Okay, we will have in the numerator, we will have 2An plus 1 half. So this is 2An plus 3 over 2. And in the denominator, we will have An Bn plus 2An plus Bn over 4 plus 1 half. And this is bigger than 1 if and only if 2An plus 3 over 2 is bigger than An Bn plus 2An plus Bn over 4 plus 1. We cancel 2An and get the condition that Bn times An plus 1 over 4 must be less than 1. This is 1 half. But this holds by induction. And in the same way, An plus 1 over 4 times Bn plus 1 equals to 1 over Bn plus 2 plus 1 over 4 times 1 over An plus 1 over 4. Okay, this is equal to Bn plus 6 divided by this expression. And this is less than 1 if and only if An times Bn plus 2 is bigger than 1, which can be shown by simple computation. Again, you will see that Bn will cancel. 6 minus 2 will give 4, 4 will cancel, and we will get exactly this condition. Okay. as I said, the consequence is that an is decreasing and bn is increasing. Now let's check that all numbers an and bn are less than 1/4 and bigger than 2. Recall is a1 is 1/3, bn is 4/3, so it holds for n is equal to 1. And now by induction, an plus 1 is 1/bn plus 2, bn is less than 2, so an plus 1 is bigger than 4. And similarly, an is bigger than 1/4, so bn plus 1 is less than 2. And this is similar to when we proved that 1/4 and 2 are smallest and largest nice numbers. Okay, now let's check this relation that an is less than 1/an plus 2, and bn is bigger than 1/bn plus 1/4. Okay, so if we multiply an by an plus 2, it will be less than 1 if and only if an plus 1 squared is less than 2, because an plus 1 squared is an times an plus 2 plus 1. But this is true because an is less than 1/3. 1/3 plus 1 squared is 16/9, which is less than 2. Good. Inequality bn times bn plus 1/4 is bigger than 1. Again, is equivalent to bn plus 1/8 squared is bigger than 65/64. Because bn plus 1/8 squared is bn plus bn over 4 plus 1/8 squared, which is 1/64. So we also need to add here 1/64. Again, this is true because bn plus 1/8 squared, bn is bigger than b1, and you can compute this number, and it is indeed bigger than 65/64. Good. One more property is 1/an plus 2 is less than 1/bn plus 1/4. But this is true because an is bigger than 1/4 and bn is less than 2. Now we're ready to prove the statement that assume that all numbers from an, bn are nice. Let's add 2 to all these numbers and get an plus 2, bn plus 2, but bn plus 2 is 1/an plus 1. Okay? And from this, we obtain that all rational numbers from an plus 1 to 1/an plus 2 are nice. Do the same with 1/4. Get an plus 1/4, which is by definition 1/bn plus 1, and bn plus 1/4, which means that all rational numbers from 1/bn plus 1/4 to Bn plus 1 are A0 nice. And now use our relations. We proved that An plus 1 less than An less than 1 over An plus 2 less than 1 over Bn plus 1 over 4 less than Bn plus 1. We know that all numbers from the segment An, Bn are nice. Of course, I mean all rational numbers. We showed just now that all rational numbers from this segment are nice, and from this as well. So we deduce that all numbers from An plus 1 to Bn plus 1 that are rational are nice. And now what we will get when we continue with this procedure. The sequence An decreases. So it decreases to some number A. It becomes closer and closer to A. And the sequence Bn increases to some number B. And the definition of An and Bn imply that A is equal to 1 over B plus 2 and B is equal to 1 over A plus 1 over 4. And from these two equations, we can find A and B. You can just check that A is 1 over 4 and B is equal to 2. Okay, so An becomes closer and closer to 1 over 4. Bn becomes closer and closer to 2. This is An, this is Bn, which means that all rational numbers from 1 over 2 to 2 without boundaries are nice, but 1 over 4 and 2 are also nice. So we proved that all nice numbers are precisely rational numbers from the segment 1 over 4 to 2. This problem can be extended. For example, the set A0 may be more complicated. Let's say it can contain 1 and irrational number root of 2. So this is an interesting research problem, how to find all nice numbers for more complicated initial sets. And in this problem, we already used iterations of the same procedure. So this problem, it has possible generalizations that can like open a door to dynamical systems and ergodic theory to you. So I hope this was interesting. Thank you for the attention. And if you have any questions, you can write me. I will leave my email probably here. So my email is Riabov George at gmail.com. So thank you once again for the attention, and bye.